recording. Okay, so we've made our way through sort of the geological background for the course, and now we're going to spend a couple of weeks on sort of the biological background. And then, when that's done, we're going to start exploring dinosaurian origins and diversity and biology and so forth. But we do need to get these sort of fundamentals in there. And one of the most important fundamentals, of course, what we know of fossil dinosaurs is their bones as well as their trace fossils. So we need to understand bones in order to proceed in this class. So yes, we got to look at anatomy. And yes, just warning you up front, buttloads of memorization here. It just can't be helped. These parts have names. You need to learn these names. And so it is what it is. Now, people have known for quite some time that organisms have, closely related organisms in particular, have the same sort of underlying blueprint. So here we see a horse, a human, a dog, a cat, and etc. Well, that's what it's labeled as. The etc. It's a cow or a sheep or a goat, a cloven hoof mammal of some sort. And all of them have a single flat shoulder blade at top. Below that, a single bone in the upper arm, then the elbow. After the elbow, there's two bones in the forearm, and then a little set of round bones for the wrist, and then some longish bones for the palm of the hand, or the front foot, if you want to call it that, and then a series of long bones to produce the toe. And we see that repeated again and again and again in these different forms. But people don't always recognize or use the same terminology for body parts, at least not colloquially. So a quick survey of the class. Which common barnyard animals have knees that point backwards? Chicken, dog, horse, cow, sheep, all of the above, or none of the above? So who here votes chicken? All right, who here votes dog? Who here votes horse? Who here votes cow? Who here votes sheep? Who here votes all of the above? Who here votes none of the above? You guys are right. Not a single animal has a knee that points backwards. The thing is, the thing that you think is the knee, when you see this prominent joint facing backwards, isn't the knee. But how do you know? Well, you have to look at the underlying architecture. Now, it's not just biologists who have to do that. It's also people from other fields, including, of all things, animators. So this is a drawing by the famous Charles Jones, better known as Chuck Jones. And even if you don't know the name Chuck Jones, he is intimately associated with the music that goes dun 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 dun, because he was the leader of Warner Brothers Studios, at least of the major animation, in their heyday. The inventor of Wile E. Coyote and the Roadrunner, the guy who modernized Bugs Bunny and Daffy Duck and company. And he needed to teach his animators proper anatomy in order for them to make a caricature or parody of them. And one of the things he would have them do is, first of all, take a human being, obviously our anatomy we know the best, and then map onto it a sock for the shin, a shoe on the foot with the sole indicated, and a little dark dot at the ankle, and then map them onto other animals. And you find out, dogs and horses have knees that point forwards, just like us. It's just dogs and horses are standing on the balls of their feet or tiptoes, respectively. And so the knee is way up close to the body, and the prominent thing you see sticking backwards is the ankle and heel. But that sticks backwards on us as well. And he did it with other animals too here. So let's see. There should be here's kangaroo, and here's a sloth. And by the way, this technique actually is still being used by animators and manga artists and so forth today. So here we see humans mapped into the position. We'll show you the skeletons here of a horse, a chicken or pigeon, I'm not certain what bird it is, a dog, and a penguin. And yes, penguins have knees. They absolutely have knees. All vertebrates, all land vertebrates have knees. It's just the knee is tucked way up here. You don't see it under their coat of feathers. Oh, by the way, horses are constantly standing on their middle fingers and their middle toes
Horses are constantly flipping people off, and if you know horses, you know this to be true. So what we're talking about here is more formally called homologies. A homologous structure is the same structure found repeated in different organisms. Or we could say literally the same body part. And comparative anatomy really dawned by understanding the existence of homology, so by recognizing the homologous body parts of related organisms. So we want to understand homologous structures, whether it's the bones or the tissues or the joints between the bones or what have you. So here we see the homologous parts of a number of vertebrates, mostly mammals, but we also see a pterosaur and a bird. And we see that all these animals have a single bone in the upper arm, a pair of long bones in the forearm, some roundish bones in the wrist, a series of longish bones in the palm of the hand, and then a series of long bones, one after another, in each of the fingers. So we'll call them fingers for the moment, but we typically call them toes for four-legged vertebrates. But they're the same thing. They are homologous to our fingers. And it doesn't matter that these structures are adapted to flight or swimming or running or grasping. It's the same underlying architecture. And other people have shown the same sort of thing. So a mastodon and a human. Or we can think about it this way. Since bat wings are just skin stretched between elongated finger bones, bats fly through the power of jazz hands. Because that's what they're doing. Their wing is their hand. Now, in contrast to homologous structures, we also have to recognize the existence of analogous structures. Structures that are a different homologous body part, but which have the same function between organisms. So here's the hand of iguanodon. And I've mapped by number, and we'll talk about that numbering system later in this lecture, the different fingers of the hand. And we have the homologous structures here. Digit 1 is our thumb, 2 is our pointer finger, 3 is the middle finger, 4 is the ring finger, 5 is the pinky. In iguanodon and its close relatives, digit 1 is a spike. Remember how I talked about when they initially found this little cone of bone, they didn't know what it was, they thought maybe it was a nose horn. It turns out it's a spiked thumb. In contrast, digit 5 in iguanodon is opposable. It can wrap around and touch the palm of the hand or the wrist. And so they would use it to pick items up. So that makes that digit homologous to our pinky. It is the equivalent body part to our pinky. But it's analogous in terms of function to our thumb. Okay. So comparative anatomy, we've encountered comparative anatomists already, and indeed most paleontologists are by definition comparative anatomists, because that's how we do our job. It's the scientific study to describe the bodies of organisms in terms of their homologous structures. So that's what we're comparing. We're comparing how their homologous structures differ from each other. And we might find that some different homologous structures have analogies in other structures of other organisms. Now, there is a specific subdiscipline within comparative anatomy that's called osteology, and that's the field that deals with the skeletons of vertebrates. And of course, since we're dealing with dinosaurs, with fossil dinosaurs, this is the main part of anatomy we need to know, osteology, because that's what gets preserved. So literally the study of bones, osteon, or osteos, bone. So bone studies. And here, it's hard to believe we're made like this on the inside. And although this is the worst drawing, well, maybe one of the worst drawings of Triceratops I've ever seen, and indeed, it's very clear if you know the museum that this is based on, that they started drawing the duckbill Edmontosaurus, and then they didn't know how to do the head, so they stuck a Triceratops head on it, sort of. But yeah, indeed, the bones in a dinosaur are the same homologous bones that we have. Sometimes they might have more of some, they might have less of others, but the underlying architecture is the same. It's the way they're shaped that's different, and it reflects different parts of their evolutionary history and their ecology. So let's think about the functions of the skeleton. An obvious one is support. Without an internal skeleton of bone, we vertebrates would be puddles of flesh lying on the ground, and that wouldn't be so much fun. So we have a bony skeleton that allows us to, in the case of Giraffatitan here, be able to look into a 4-story window and so forth. It can act as the protection for important internal organs. So our brain is located inside a brain case. Our ribs and heart are protected by a rib cage, and so forth. And they are mechanical structures. The way our bodies work is by a series of levers. By work, I mean sort of mechanically work. It's a series of levers where muscles are attaching to bones on the opposite side of a joint and provide our operation. Now, the skeleton is interconnected. Well, first of all, bones are connected at either mobile joints, so a connection that moves, or at sutures, which might be more or less mobile. So, for instance, the sutures of our brain case are not particularly mobile. Let's say hopefully not, especially as adults. Whereas the bones in our leg hopefully do have joints between them to allow our legs to move. Now, when we find skeletal material in the fossil record, it's mostly the bone, mostly permineralized bone that we find. And we don't find the softer tissues that were there before. Now, in life, the sutures and joint surfaces would have been covered by the soft tissue cartilage, which does occasionally survive. And the bones connected by ligaments. And that's why if you just fleshed out, so removed the flesh of an animal, you could still have a skeleton that hung together because of the ligamental connections and the cartilage in there. So there's mobile joints in the hind limb of a tyrannosaur called Tarbosaurus, and there's individual sutures in its skull. The skull is not a single bone. The skull is comprised of multiple bones that fit together, sometimes very loosely, sometimes very rigidly. Now, skeletons plus muscles give us sort of the functional machine-like aspects of an animal. And here we see a reconstruction of the homologous muscles in the neck of a dinosaur. We could use the homologies to modern relatives, birds, living parts of Dinosauria, and also crocodilians, and then lizards and other relatives, to figure out which muscles attach where. And by the way, muscles attach to bone with tendons. Now, a muscle can only pull, it can't push. A muscle only has power in contraction. And in fact, the way we move is the fact that almost every muscle or cluster of muscles has a corresponding cluster of muscles that work in the opposite fashion. So for all the jaw closure muscles, there's a set of jaw opening muscles. For all the muscles that allow me to bend my arm like this, there's another set that pulls it back this way. I don't have to simply wait for these muscles to then relax and let the arm flop back down. There are antagonistic, as we say, or opposite sets of muscles to allow the body to work as a machine. Okay, now, brace yourselves. Now we're going to get to the real terminology part. In order to navigate around the skeleton, we need a sense of direction. And there are indeed what we call anatomical directions. Now they describe the relative position of different bones or other body parts to each other. Consequently, they're actually very similar to navigational directions. So if you're familiar with, say, going out on boats, in a boat we talk about fore and aft, so front and back, port and starboard, left and right. And we do that because those are internal to the boat. They don't rely on the coordinates on a map. So fore is always in front of the boat. Doesn't matter which way the boat's headed. Similarly, the anatomical directions are the same. They're internal to the organism. It doesn't matter its orientation in space. It doesn't matter if it's a snake all coiled up. They're internal to the organism, and much like fore and aft and port and starboard, all anatomical directions come in pairs, complementary pairs. So here we go. The first major set of directions, anterior versus posterior. And by the way, if anyone has taken some like pre-vet class or maybe some pre-med type classes, you might hear slightly different use of the terminology here. That's slightly different than standard zoology. This would be cranial and caudal, but I'm just going to use anterior, posterior for this class. It's traditional. Anterior means towards the tip of the snout, so forwards. Posterior, towards the tip of the tail. But these are relative to each other. So, you know, this bone right here is anterior to this bone, and this bone is posterior to that bone, even though they're all in the same front end of the animal. Oh, I should point out too, at this point, notice that anterior, posterior, some of you who might have taken a Romance language or actually did take Latin, anatomy, modern anatomy was developed actually in the Middle Ages and the Age of Enlightenment. It relies heavily on Latin or Latinized words. So if you know Latin or Latin-like language, Latin-descended languages, a lot of these terms will be familiar. And we can talk about anterior and posterior just within the skull. You know, anterior towards the tip of the snout, posterior towards the tip of the tail, even though we're in the skull. Okay, next pair, dorsal and ventral. Now this is one case where we humans are super duper weird. We walk in a strange fashion. Even in terms of bipedal, two-legged animals, we walk in a weird fashion. A baby gives you a better sense of the proper, from the point of view of the rest of vertebrate, orientation. So think about on all fours like that. Dorsal is out through the back, up and out through the back. Ventral, down and out through the belly. And again, we could do that within the skull, you know, dorsal and ventral on this skull. So these spikes are dorsal to the vertebrae here, and the heart would have been ventral to the vertebrae in life. Everyone with me so far? Cool, awesome. The next pair, medial and lateral. We vertebrate animals, and indeed many types of animals, are essentially bilaterally symmetrical. We have a midline plane, or a mid-plane, sagittal plane down the body, and mirror images of most body parts on the left and the right. So medial is towards that midline, and lateral is away from that midline. So, for instance, the heart would have been medial to the ribs, and the shoulder blade is lateral to the ribs. If the heart somehow wound up lateral to the ribs, you'd be in a very, very, very bad condition. That would mean your heart's outside the ribs, and that's not a good thing. And again, you know, we don't have to do just the skeleton, we do the skull, medial towards the midline plane of the skull of this T-Rex, and lateral away from it. Now, if this was a course called Snakes, A Natural History, we actually wouldn't have to matter about too much of the next one. But there's one more set of directions. Yeah?
So this only works for like bilateral?
Correct. The question was, this only works for bilateral organisms? Absolutely. But since we're a course on vertebrate osteology, and a particular sort of vertebrates, it'll work for us. If we were talking about sponges, if we were talking about corals, if we were talking about starfish, total different set. You ever take an invertebrate zoology class, or you take Principles of Paleo with me, we'll go over the other terminology we use for those sort of critters. So, organisms with limbs, we have to deal with another set, and this is proximal, which is towards the trunk. That's the main part of the body. Not like an elephant, but the trunk like the main part of the body. And distal is away from the trunk. So your wrist is distal to your elbow. And your shoulder is proximal to your elbow. And this end of my fingernail is as distal as I can get. Now, proximal and distal are used for the limbs only. Sometimes people will, and I will admit, I will do this out of a reflex occasion, use it incorrectly for the tail. But the tail is technically not a limb, it's part of the axial skeleton. That's the main trunk of the body. So you should only use anterior and posterior when talking about the tail. And again, this is internal to the organism. It doesn't matter if, I've wrapped, some sort of yoga person, and I've wrapped my hand around this. My finger, the tip of my finger, is still always distal to my wrist, no matter what position I get it in. Yeah?
Can you give me another example? I'm not really understanding, what you mean by the trunk.
The trunk is just part of the body. The main axis of the body.
Oh, okay.
Head to tail, so head, neck, torso, hip region, all the way out to the tail. Got it? Okay, great. All right. Now, another thing we have to think about is anatomical views. What parts, or what direction are you seeing it from? Often, if you're reading a paper, it'll tell you that you're seeing this bone in right lateral view. And what do we mean by that? It describes which surface you're seeing. So, lateral view would be a side view, and since we're bilaterally symmetrical organisms, we as dinosaurs, we have a left lateral view, that is, you're seeing my left side, and a right lateral view. Here we're seeing the left lateral view of a Margosaurus. Here's a right lateral view of Allosaurus. There's anterior view. You're seeing the front end of the skull. Although we could look at the anterior view of a vertebra, we could potentially look at the anterior view of the posterior-most vertebra, and it would still be anterior view. Or here we get an example. Posterior view, the butt end view of Brontosaurus. The tail has been removed, so you're seeing the actual butt area. Left lateral view, dorsal view, sort of a pterodactyl's view. Dorsal view, you're seeing the top of it. An anterior view, although the head has been chopped, the head and neck have been chopped off, so that's the anterior view of the chest. Or we can look just at the skull. Left lateral view, ventral view, the underside. In this case, there's a special name, if you just want to know, in case it slips out by accident for me sometime. The ventral view of the mouth is called the palatal view. You're looking at the palate, but you don't need to know that. It's ventral view. Posterior view of the skull, dorsal view of the skull. Everyone comfortable with this so far? Got a question?
So ventral is underneath?
Ventral is you're looking at the ventral surface, the underside surface. Exactly. Good question. Okay, now in navigation we need more than directions. We also need landmarks. And it's true in anatomy just as it is in navigation. Landmarks are particular homologous structures, like maybe openings or joints or something like that, that are useful for identifying the position of bones and other anatomical features. An example of that, the eye socket, which in a few minutes you will learn the proper name from, is a good landmark. By the way, do remember that we're recording all this, so you can always watch them online too. No problem with doing that, that's fine. It's a good way of taking notes, but just making sure that you were aware of that as well. Good. Okay, so the orbit, spoiler alert, the eye socket is a useful landmark in the skull of vertebrates, since most vertebrates have it. Or the nares, or the opening for the nostrils. It's another good landmark. By the way, one of these dinosaurs is in a different view than the others. What view is it in? Go for it. Right lateral view. Right. Dilophosaurus, because it's a carnivore, decided it didn't want to hang out with this bunch of herbivores, so it is in right lateral view down here. Okay. So now, the names of the body parts. First, we're going to divide the skeleton into two parts. They're not two equal parts by volume, but in some ways they're almost two equal parts by complexity, and that's the skull and everything else. But to make everything else sound more Latin-y, we call it the postcranium, posterior to the cranium, behind the head. So skull and postcranium. So that's one way of splitting it up. And another way, particularly useful when we're talking about the postcranium, is to talk about the axial, first of all, the appendicular skeleton. An appendix, not in a biological sense, but just in that word itself in Latin, is that which is attached to. So the appendicular skeleton are the things attached to the axial skeleton. These are the limbs, the front limbs and the hind limbs, the arms and legs, if you will, and the girdles that attach the limbs to the body. This would be the shoulder material and the hips. And then the axial skeleton is the trunk of the body. Essentially the vertebral column, the ribs, and anything else that's down this main axis of the body. So the way we're going to work through the anatomy, we'll start with the skull, then we'll do the axial skeleton, and then we'll do the appendicular skeleton. Yes?
Would the skull be considered appendicular or not?
No, it would be part of the axial skeleton if you wanted to call it that way, because it's down the main axis of the body. So, the skull is made up of many, many different parts. And if you've ever studied human skulls, maybe you did in a pre-health class or something, or an actual pre-med class here, you would learn there's lots of different parts. Human skulls actually have fewer parts than a lot of other animals. What's happened is homologous bones and other animals tend to be fused together. We have more fusion in our skull than a lot of creatures. On the other hand, as I walk through dinosaur skull anatomy, it is less complex than fish. I am on record as saying fish have too many skull bones, please eliminate them. And actually in evolution they did. So here's a look at what I call an exploded view of a tyrannosaur, the Splendosaurus, with the skull bones separated from each other. And this little animation here, you can see the exploded view on one side and the connected view on the other. So all the different skull bones have names. All different bones, period, have names. So let's start working through it. Let's start first, actually, with the two major sections of the skull. The cranium is the upper part of the head, and the mandible is the lower jaw. So, if we were talking about mammals, like humans and other mammals, the mandible is made up of only a single bone. But in the vast majority of vertebrates, it's made of multiple bones, and dinosaurs included. So cranium versus mandible. Next, let's do some of the major landmarks. The orbit, or eye socket. Typically very conspicuous. You can see where the eyeball fits. It would be surrounded in there by muscles that control the eyeball and so forth. And the nares, the opening for the nasal passage. Now sometimes people will refer to the nares as the nostril. Technically speaking, it isn't. The nostril is a fleshy opening. In many cases, the nostril is there in the front part of the nares, but it's not always the case. Think about an elephant. Its nostrils are like many feet away from where its nares is. So they're different things. And as the air passage, the nasal passage goes from inside the skull, then out through this hole to the outside world, or from inhaling the other direction. By the way, nares has a Latin plural, nares, and all of these are described in the lecture notes online. Now, so my orbit is here, my nares are here. My anterorbital fenestra doesn't exist, because I'm not a dinosaur or a close relative of a dinosaur. Not all homologous structures are found in all groups of organisms. And one particular feature that characterizes dinosaurs and their cousins is an extra opening or window, and we use the Latin word for window, fenestra, that is anterior to the orbit. And so it was creatively given the name antorbital fenestra. In life, there's a sinus that goes in there. We'll talk about that later on. Right now, we're just doing the anatomy. There is another fenestra down here in the lower jaw. Remember, fenestra window. This is the mandibular fenestra. And it houses a big muscle. One attribute of muscles is they always retain the same volume, whether they're stretched out or contracted. And by opening fenestrae for some muscles, it allows the muscles to expand outwards, and so they can be bigger and more powerful than they would be if there was a wall of bone that was preventing them from expanding outward. And that's what's going on with the mandibular fenestra. Now some of the individual bones. There are three major tooth-bearing bones in the faces of dinosaurs and mammals and most other toothed vertebrates or toothed land vertebrates. In the upper jaw, there are two of them, the maxilla and the premaxilla. And I should point out, essentially all skull bones have a left and a right. So the maxilla is the typically larger of the two. It is definitely the posterior of the two. The premaxilla is in front of it. In our case, our premaxillae have our incisors, and our maxillae have the canines and everything back. Canines, bicuspids, molars, as we call them in humans. In the lower jaw, there's one tooth-bearing bone, well, on each side, and that's called the dentary, or tooth bone. In the case of us mammals, that's all we have left in our lower jaw, is the dentary. We have to just call it the mandible for the most part, but it is homologous to the dentary here in a dinosaur. So premaxilla, maxilla, dentary. That said, if the maxilla or the dentary or the premaxilla lose teeth, they are still a premaxilla or maxilla or dentary. And they will lose teeth in some groups. But ancestrally, they had teeth. Now, on the dorsal surface of the skull, dorsal to the maxilla, dorsal and posterior to the premaxilla, is the nasal. One on each side, nasals. Oh, I should say maxillae, premaxillae is plural. So the nasals. In us humans, the nasals are not particularly big. They're little bones right here. But dinosaurs tend to be long-snouted animals, and they tend to have pretty long nasals. Between the orbit and the anterorbital fenestra is the lacrimal. If you've studied Latin, or if you've sung a Latin mass, you know the lacrimosa, which refers to tears. This is the bone where the tear duct comes out of, or around. We have our lacrimosa right here. And just to show a couple more bones here, we're not going to belabor them because you'll have charts in the notes and so on. The jugal is the cheekbone. In the back of the skull, there are a couple other ones. The squamosal, the postorbital, not surprisingly posterior to the orbit. The quadratojugal connects the jugal to another bone called the quadrate. And there's a couple post-dentary bones in the lower jaw. Don't worry about them too much right now, just putting them on this figure so you can see them. But let's take a look at the skull from multiple dimensions. Those are the nasals here that we saw before. Behind the nasals are the paired frontals. In us, the frontals right here. Huge bones in us, smaller in them. The frontal lobe is the part of the brain right behind that, hence frontal lobotomy if you got it cut out. And behind the frontals, the often fused parietals. And so the brain sits underneath the frontals and the parietals in here. Dinosaurs, not as big a brain as ours, obviously. We have huge frontals, gigantic parietals. There's the quadrate in the back of the skull, the posterior view. It's the bone that actually connects the upper jaw to the lower jaw, at least in dinosaurs and most other vertebrates, not as mammals. The quadrate. Now, the brain case isn't just one bone, it's a series of bones. We are not going to learn the names of the bones of the brain case in this class. That's a 400-level thing. An important landmark in the back of the skull, the foramen magnum. Foramen is an opening. Magnum is great, so it's the great opening. It's the way that the spinal cord, the spinal nerves, come out of the brain and connect to the spinal cord for the rest of the body. And it's so important, it was called the great opening, because without it, the rest of the body couldn't communicate with the brain, and you would be dead. Now, there's a little rounded knob that connects to the vertebrae, or the vertebrae pivot against it. Rounded knob in Latin is condyle, and it's in the back of the skull, which is just generally called the occiput region. So it's the occipital condyle. So it's the rounded knob below the foramen magnum, and it's held in by like a cup in the front end of the vertebrae. Now, a couple other important fenestrae. There is what's called the infratemporal fenestra. Okay, one moment, yeah.
What does the occipital condyle do?
It's the rounded knob that the skull connects to the vertebrae. It allows the skull to pivot back and forth against the vertebrae.
Thank you.
Sure. So, I should say temporal, this part of the head is called the temporal region, the temple. And it's where lots of jaw muscles attach. In fact, if you put your fingers right there, put your fingers there, and shoo up and down, you can feel muscles bulging in there. Those are our temporal muscles, temporalis muscles. In these forms, there is a fenestrae, or actually there's two fenestrae, that allow these muscles to expand outwards. The lower of the two is called the infratemporal fenestra, the lower temporal fenestra, or the lateral, because you see it from the side view, temporal fenestra. So it's that window right there. And muscles go from the lower jaw, and they emerge out on the outside there. And then there's another set of fenestrae, a left and right. I don't know why. There we go. Getting rid of some names. The supratemporal fenestra, the top temporal fenestra. And it occupies that volume. Now, technically speaking, one moment. Technically speaking, we mammals have an infratemporal fenestra. This whole region here on us is homologous to the infratemporal fenestra. We do not have a supratemporal fenestra that evolved independently, in the group that includes dinosaurs and turtles and lizards and snakes and crocodiles and birds. Yeah?
I was going to ask if these features are present in mammals.
They're not, yeah. The infratemporal fenestra is not the supratemporal fenestra. That's a story we'll get to. Okay, now let's go inside the skull. Inside the skull is a brain cavity. It's the space in which the brain sat. And we could see with these CT scans, the stuff in blue is basically the brain. And you can see it doesn't occupy that much volume in many dinosaurs here. Somewhat larger here in these advanced bird-like dinosaurs. Here it would occupy in Stegosaurus. But thankfully, actually, the nerve spaces coming out, the holes for the nerves coming out of this brain cavity are conserved. That is, they are found the same in many groups of modern animals, so we can map out which nerves are coming out of which part of the brain in a dinosaur, as just we can a modern animal. Okay, let's talk about the teeth. Each tooth in a dinosaur is in a socket. It has a root that extends into the socket and a crown that sticks out of it. The crown of the tooth is covered by a special type of bone-like material called enamel. And enamel is the very toughest material that a vertebrate body can produce. So teeth preserve typically very well. So much like you and I, the teeth are in sockets in a dinosaur. However, unlike you and I, but like the vast majority of non-mammalian vertebrates, they continue to get new teeth out of each socket throughout their life. We get two. We have our baby teeth, it falls out, an adult tooth comes in, that's it. It's a mammalian trait. Almost all the other groups of vertebrates, you get one tooth, it falls out, another tooth replaces it falls out, another tooth replaces it, all throughout their entire life. So now let's move to the axial skeleton. The fundamental part of the axial skeleton is the vertebral column, all the vertebrae together. We call it a column because we got to name it and we stand like this. So it basically is a column. In almost all of the vertebrates, it's a column that's lying horizontally, essentially, which we wouldn't call a column. But we do because of tradition. It's made up of individual vertebrae. So here is a vertebra. Singular vertebra, multiple vertebrae. Unlike what every person thinks, I did too before I learned this, the nerve cord doesn't go through this part. It doesn't go through the middle of the vertebra. It's not going through there. Instead, it's a passage above that. That's called the neural canal. And the neural canal is formed between the centrum, or literally the body of the vertebra, that's that spool shape, or typically spool-shaped section, and a neural arch that extends above it, and they form around the neural canal. They actually start as separate bony parts and fuse together as the animal gets older. Sticking out of the neural arch are lots of prongs and processes, and I'll just highlight a couple of them because they're important. Going dorsally from them is the neural spine. That's the one part of the vertebral column you are likely to touch. So when you feel the bumps on the back of your neck, particularly when you go from the neck to the shoulder, you feel those bumps, those are your neural spines. Sticking out laterally are what we call transverse processes. And lots of different muscles attach to the neural spine and transverse processes, and they allow the body to move back and forth and up and down and all sorts of things. All the action down that main part of the body. The vertebral column is broken up into several segments. In the case of dinosaurs, we typically think of 4 sections, and that's true of most land vertebrates. They're named after the part of the body they represent, but they represent it in Latin. So the cervical vertebrae or neck vertebrae. The dorsal vertebrae or backbones. The backbones of the back, the dorsum. The sacral vertebrae of the hips. In most dinosaurs, the sacral vertebrae fuse together. And when they fuse together, we call them a single thing. We call them the sacrum. Although it's made up of individual fused vertebrae. And then the tail vertebrae are the caudal vertebrae. Cauda, in Latin, is the source of the Italian coda. So if anyone reads or plays music, you know the coda is the thing at the end of a piece of music, often it repeats. Same word, just at different phases of history. So cervical, dorsal, sacral, caudal. And here we see again those body parts. Centrum, neural arch, together forming a neural canal. Neural spine coming out, and transverse processes shown here but not labeled. Some other axial features. The ribs. Ribs and skull are the 2 major body parts where in English we use the English word, good old-fashioned Anglo-Saxon word. We don't say costae, even though that's the words in Latin. And we don't say calvarium for skull typically. Sometimes we do it. Just an aside. Ribs actually do have a Latin word, but we use the English word ribs. The ribs connect to the vertebra by typically soft tissue connections, although in a few groups they actually fuse. And then the belly ribs. Well, I can't point to them on meat because we don't have them anymore. But many types of vertebrates have a series of what we call gastralia, or belly ribs, that extend down the mid part of the body. We'll talk about the function of gastralia, at least in archosaurs, dinosaurs and their kin, in a later lecture. On the tail, instead of having gastralia, or ribs, they have what we call chevrons. Chevrons are so called because in dorsal or anterior or posterior view, they look like little chevron structures, like the stripes on a sergeant. And they're sort of upside down versions of a neural arch. They protect the blood vessels and nerve vessels running on the underside of the tail. Also, in at least some dinosaurs, there are parts of the skin that form bone, and they're called bone skin, osteoderms, or armor plates. To be fair, osteoderms can also form in the appendicular skeleton, but I had to talk about them somewhere, so here they are. Now, the forelimbs, or pectoral girdle, and forelimb. The pectoral girdle, or shoulder girdle, is made up of several different elements. The largest bone is the scapula, or shoulder blade. It's the largest bone in our pectoral girdle as well. In dinosaurs and most other land vertebrates, not so much we mammals, there's another bone in the main part of the pectoral girdle called the coracoid. In us, it's shrunk up and fused up. The scapula and coracoid start as separate bones, but in growth in dinosaurs, they tend to fuse together. And then the shoulder joint is actually typically on the back side, the backward surface of these two. So the arms of dinosaurs typically stick backwards somewhat. Now, In us, we have paired clavicles or collarbones. Some dinosaurs seem to have paired clavicles as well, but in at least the carnivorous group of dinosaurs, they fused into a single bone called the furcula. Furcula is the Latin word for the wishbone, and in fact, birds retain this fusion. Okay, full disclosure. There is a minority opinion, but one worth considering. I talk about it in the lecture notes, that actually the furcula is derived from another element in the pectoral girdle. For this class, we're considering it to be clavicles, but you can read more about it if you want. Here we have it again from the side. So we've got the scapula, the coracoid. Now we're going to march down the arm. There is a single large upper arm bone, that's the humerus. Through an amazing twist of fate, the humerus is not the funny bone. Okay, it's true though, it is not the funny bone, despite the fact it is spelled similarly. Not the same, there's no O in humerus. Then, after the elbow, the forearm has two bones. The larger and more typically ancestrally more posterior of the two is called the ulna. And the back of the ulna is actually where the funny bone is. The more slender and typically more anterior of the two is called the radius. Radius is just the Latin word for a spoke, like a spoke on a wheel. And to know why it's called that, you hold your arm out and you twist your hand back and forth like this. The ulna is staying in place, but the radius is moving. The bone right here. The wrist is made up of individual carpals. I'll expand this in a moment. Well, actually, I'll expand this now. Look, before I get there. In us and other mammals, we tend to have a fused sternum or breastbone. In dinosaurs, the sternal plates, the individual flat plates, typically do not ossify. They're typically cartilage, but sometimes they fuse as individual sternal plates, and in a few cases we'll see they fuse into a sternum, a single breastbone. Okay, here we have the manus, or hand. By the way, manus, singular, plural, manus, but spelled exactly the same. It consists of a carpus, or wrist. The wrist is made up of individual carpals. Now, the individual carpals have names. You're not going to have to deal with those. Or wrist bones. Carpal tunnel syndrome is a condition some people get with repetitive motion of the wrist. And then what's tunneling there is a tendon that's tunneling into one of the bones. The palm of the hand, which is encased in flesh, is called the metacarpus. And it's made up of individual metacarpals. And we count them from 1, count Roman numeral 1 as the medial most, to 5 for the lateral most. 1, 2, 3, 4, 5. So metacarpals. Each finger is a digit. And the digit is counted 1, 2, 3, 4, 5, same as the metacarpals. It's comprised of individual phalanges. The singular of phalanges is phalanx. The plural of phalanx is phalanges. Those are individual finger bones. And finally, for the hand, and for this lecture, well, it's for the live part of this lecture, the distal-most claw or hoof-bearing phalanx is called an ungual, or claw bone. So the ungual is a phalanx, but it's the distal-most one if it actually has a nail or a claw or a hoof on it. So manus, the adjective, manual. That's where we get that word, manual, of the hand. Carpals, metacarpals, digits, 1, 2, 3, 4, 5, made up of individual phalanges. We only have a little to go, but rather than have it spill over to next lecture, I will record the pelvis and hind limb online. It shouldn't take too long, but it is, I'm saying out loud, extraordinarily important for dinosaur studies. Both the pelvis and the hind limb we will be referring to again and again and again. So after I record it, please make sure you watch it. It's going to be on the homework this week anyway, so you'll want to know it that way. So take care. See you in class next time where we'll begin to look at this weird and wonderful world of names for species. And yes, more Latin.